Hey everybody, welcome back to our video. This is the fourth in this playlist. This one is going to be talking about the correction step in the Kalman filter. The correction step is also sometimes known as the measurement update. In the running average example that we did with the resistor, the update implicitly assumed that all the measurements were corrupted by white noise. We would model this mathematically in the following way. The measurement Z is equal to the true state plus some measurement noise. Here V at time K is the measurement noise at time K. Now when we're doing simulations, we assume that we know the truth, and therefore we can generate simulated measurements by adding normally distributed measurement noise to the truth at each point in time. Measurement processing is sometimes called observation processing. Because the measurement noise was assumed to be normally distributed or Gaussian and to be zero mean, our best guess was simply to average the value of all the measurements. So in the voltmeter example, we assumed that the voltmeter was not perfect. We assumed that therefore it would produce an unbiased estimate, but a noisy one that gave us the true value of the resistance plus a disturbance that came from randomness in the voltmeter. Note that that randomness is always assumed to be completely independent of any noise that might be in the thing that's being measured, i.e. the dynamic process itself. We haven't dealt with process noise in any of our processes yet, but we will, and that's something that Kalman filtering will take into account. But in any event, the process noise is assumed to be independent of the measurement noise. We further complicate general Kalman filtering by adding some new elements to the measurement model. First, we assume that the measurement relationship could be a little bit more complicated. We might have a general function h, which maps the state at time k into the measurement at time k. In order to compute the Kalman gain, however, we're going to need this relationship to be a linear one. So h will typically be a matrix. But we can generally always derive a matrix from the h function if we have a nonlinear function, if we assume it's differentiable, therefore smooth, and so we can compute a Jacobian matrix. So the h matrix generally in a nonlinear situation will become the Jacobian matrix at that point in time. Also, we complicate things by saying that just as x can be a vector state, we can also have a vector of measurements. This is actually very useful because that allows us to engage several different measurement sources at the same time. We can have multiple sensors all measuring the same thing, but from different perspectives perhaps, and perhaps also independent quality. And yet treating them as a vector, stacking them together into a single column vector for Z will allow us to deal with all those measurements simultaneously. That's why the Kalman filter is sometimes referred to as a sensor fusion algorithm, because we're actually taking information from multiple sensors and fusing them together. Also notice that this equation is an algebraic one or a functional one. It's not a differential equation or difference equation. That's because we're taking a measurement at a particular point, a snapshot at a particular point in time. The measurement is not dependent in any way on previous measurements. All the time dependence is captured in the process model, the difference equations and differential equations. So, if you think back to our running average example once more, you can recall that we used the measurement to update our last estimate. So we had an equation that looked like this. The updated measurement x hat plus was equal to the estimated measurement or estimated predicted estimate, which is x hat minus, plus a small increment that was a weighted value of the difference between the actual measurement and what this predicted state was or predicted measurement. Note that in this case with the resistor, we used x hat minus in the measurement residual. Ordinarily, we'd have to apply the h function to it in order to get the actual measurement in the units or coordinates that the measurement is in. So that's what the H matrix does. Now, as we mentioned before, if we had more than one voltmeter or sensor, we could take simultaneous measurements and then stack them together into a column vector. So we would have a measurement model that looked something like this. Here we have two measurements from two different voltmeters. The relationship is very simple still. It's the H matrix here is an identity. And then we add on to it the measurement noise. And those are separate independent measurement noise samples for each voltmeter. They might have identical statistics, but they're independently sampled. So here the H matrix is a simple 2x2 identity matrix. And the noise, the actual noise values would be different unless the units were considered to be identical. Then they would be identical in statistics, but not necessarily in sample value. The solution of the Kalman gain, which we'll talk about in the next video, assumes that H is a matrix. And so we will typically use the capital letter H to indicate this measurement matrix. So let's see where we are. We've discussed the measurement model and how estimates are updated using measurements. We've talked about how that applies in the running average example with the resistor. And so in the next video, we're going to take a look at the Kalman gain in more detail. And we'll see how that gain is applied to the measurement residual. So we will drill down a little bit more on that concept as well. So thank you for watching. We'll see you in the next video.